Hey everybody, welcome back. If we're going to build an artificial intelligence model, then it needs to be intelligent. And so it should probably be modeled after, humans who are fairly intelligent. Now, we're intelligent because we have brains, and our brains are made up of a network of biological neurons. Well, we can't quite make our own biological neurons in a lab, at least not very easily, but we can kind of mimic their function artificially on a computer with a network of artificial neurons. It stands to reason, the basic building block of AI then is the neuron. And we'd like to see how far just a single neuron can get us. Is a neuron capable of mimicking a logical function, right? If you want an artificial intelligence, then it at least needs to be logical. So we'll look at some very simple logic functions and see whether a single neuron can mimic those functions. Let's see how this could be done. Let me grab a pen. All right, so let's remind ourselves, what's a simple neuron look like? It takes a couple of inputs, x1 and x2. We apply some weights to those inputs, W1 and W2. We aggregate them, right? A linear product or a dot product. And then after that, we apply a nonlinear activation function, a step function. If the value of this sum is bigger than 0, it's going to spit out a 1. If not, it's going to spit out a 0. And let's call our guess, by the way, rather than a y, let's call it a y hat. All right, now, how can this simple construct mimic a logic function? And for that matter, what the heck is a logic function? All right, well, the simple logical statements are things like, if A is true, and B is true, then C is true. Something like that. Now, in the computer world, true and false, those are binaries, and so the simplest way of doing a binary is with a 0-1 variable. All right. So this is an input. A is true. This is an input. So this is like x1. This is like x2. And our output, that's going to be like our y. So we need combinations of zeros and ones to spit out the appropriate combination of zeros and ones. So we can go through an entire list. Like if we had we had A, or let's just call it x1, so we're consistent with this notation. We have values for x1 and we have values for x2. Then, well, we could have 0, 0. We could have 0, 1. 1, 0, and 1, 1. Those are the 4 possible combinations of values for x1 and x2. We could repeat ourselves, but this is sufficient. And then how can we mimic an AND function? Well, so what do we mean by AND? What we mean by AND is if both things are true, if A is true and B is true, so if x1 is true and x2 is true, then y1 is also true. But otherwise, they're all not true. It takes both A and B being true to make y be true. That's what we mean when we say an AND function. So this kind of representation of the AND statement is called a truth table. A truth table takes an exhaustive list of all the possible inputs and gives you what the true-false values of those combinations are. And since we only have 2 inputs and they're binary, we could only have 4 combinations, and that'll give us these values. So this truth table defines what we mean by the AND function. Our big question is, can a neuron like this with appropriate weights and bias, can this thing inside this square, as long as we got the right W's and the right B's, give us this truth table? Well, it turns out that you can. You just got to have the right weights and biases. So let's try some on for size. All right, so we have W1, W2, and B. And these need to have, there's got to be some values of these weights and biases that if we feed it through this kind of function will give us the appropriate outputs. Let's try 1, 1, and negative 1.5. Okay, will this work? Well, let's aggregate everything together. So we take our linear sum, our weighted sum of our inputs. Let's tack on a bias and then see whether this thing is positive or negative. Now, what values do I put in? I know what my values are for W. That's 1. And for W2 is also 1. And B is negative 1.5. So we have x1 plus x2 minus 1.5. But what values do I feed in here for x1 and x2? Well, it depends on the situation. We have 4 possible situations to check. So we need to go through this exercise 4 times and see whether this list of parameter values, of weights and biases, is enough to make this neuron behave like this truth table. All right, so let's apply this formula, this neuron, to these 4 cases. Let's call these A, B, C, and D. All right, let's try this. We got case A. All right, so x1 is 0, x2 is 0. So what is Z? We have 0 plus 0 minus 1.5. That's just minus 1.5, which is a negative number. And so our prediction is going to be a 0 because it's negative. So our step function says if Z is a negative number, we're spitting out a 0. All right, so this is our guess. This y hat. This y here, this is our target. This is what we wanted to get. And so our guess, our model's output, 0, matches up with the desired target. So our neuron satisfied case A for the truth table. So we're good. What about case B? Well, case B, we have a 0 for x1, but a different value for x2. And when we plug this into our neuron, we better hope we're going to get out a 0. Let's see. All right, so we start plugging in stuff into our z function. x1 plus x2 minus 1.5. What is x1? x1 is 0. x2 is a 1. So we get 0 plus 1 minus 1.5. So that's 1 minus 1.5, which is minus 0.5, which is also negative. And so our step function says, hey, if you get a negative z from here, then we're in the 0 part of that step function, and we get a 0 for our guess, and that is exactly what we wanted. And so we're good. We have mimicked the first 2 cases. What about case C? Now we're going to have a 1 for x1 and a 0 for x2. So we plug in a 1 here, a 0 there, minus 1.5. We have 1 minus 1.5, again giving us negative 1/2. And so we also get y hat is 0. That's what we wanted. So far we're really good. All right, what about case D? All right, now we're going to plug in a 1 and a 1 for x1 and x2. So we get 1, 1 minus 1.5. That part gives us 2, minus a half. Gives us a positive a half. That's a positive number. So y hat, our guess is, our output is a 1. And that is indeed what we wanted. So we've now just shown that this particular set of weights and bias, when applied to this neuron, this guy here, mimics exactly the AND logic function. That's pretty cool. Now it turns out that there are other weights and biases that will do the same thing. They don't all do it, but there are other options. So let's just work through one other set of such parameter values. I'm going to erase my board, recopy over the truth table, so give me a moment. Okay, so we're back. I've copied over the truth table for the AND function, and we're going to try out this different set of parameter values. We'll see that this particular set also mimics AND. Not all of them will, but this one will work. So let's remind ourselves what our neuron is. Now, rather than doing this graphically this time, I'm just going to jump to the formulas. The formulas first involve the linear part, the aggregation part, which is a weighted sum. And then the nonlinear part. If z is positive, we're going to guess 1. If z is negative, we guess 0. So that's our neuron. And now let's consider all 4 cases, A, B, C, and D. All right, so for case A, what is z going to be? It's going to be 0.8 times 0 plus 0.8 times 0 minus 1. Which means z is negative 1, and since that's a negative number, since z is negative, we spit out a guess of 0. Yep, that is correct. What about case B? We got to plug in 0 and 1 for x1 and x2. So here we get a 0 plus a 0.8 minus 1. That is a negative 0.2, which is negative. And so our guess then is going to be our output is also a 0. And that's exactly correct. Case C. We got our weights. And this time for case C, x1 is 1, x2 is 0. All right, so that leaves us with 0.8 plus 0 minus 1, which is also a negative 0.2. That's a negative number. So our output is, again, 0, which is correct. That's what we wanted. Our guess and what we needed to be correct, they're the same thing. And then finally, the interesting one, I think, is case D. 0.8 times an x, 0.8 times another x, minus 1. Our x's are now both 1s, so let's plug those in. So we get 0.8 plus 0.8 minus 1. That is 1.6 minus 1, which is 0.6, which is positive. Positive numbers give us a 1, firing of our neurons. And so sure enough, that's exactly what we needed to be the case. So this set of parameter values works just as well as the previous one that we did. Okay, if you were to try some different weights, chances are pretty good that you would not get would not be able to mimic this truth table. All right, so let's just try, I'm going to just try a random set of numbers and see if I can't break this thing. Switch colors to red this time. And rather than 0.8, let's have, I don't know, let's try 0. All right, so let's try it. So our function is W1, which is now at 0, times x1, plus 0.8 is our weight for x2. So we're going to times x2, and then plus b is our -1. So this is the function we're going to be working with. We now have a new weight to contend with. And I think that's going to be enough to break this neuron so that it doesn't reflect an and function. So let's try it. Maybe the first one will work. In fact, I'll almost guarantee the first one will work. Let's see here. Plug in a 0 and plug in another 0. So we get 0 plus 0 minus 1. That's negative. All right. So this one is still good. Will it break? It won't break B. Let's jump to C. I think C is going to be the case that breaks us. So we need to fill in x1 and x2. x1 is 0. x2 is 1. Oh, sorry, we're doing C. x1 is 1. No, C is going to work. So it's going to be 0 plus 0 minus 1, which is negative. That's going to give us a 0. What about case D? Is case D going to break? Let's see. We got our weights. We got the bias. Our inputs are 1 and 1. So we get a 0 plus a 0.8 minus 1 is 0.8 minus 1, which is a negative 0.2, which means that we're expecting a 0. Negative gives us 0. And so for case D, I'm not able to replicate this 1. Instead, I got a 0. And so we can see that this new set of parameter values will not replicate the and, but the original set will. All right, so the lesson here is all it takes is a single neuron and the appropriate weights, and then we can mimic the logical function that's called and. A different set of neurons will allow us to mimic different logical functions. Unfortunately, it's not going to be the case that there's a set of weights and biases where we can mimic any logical function, but we can mimic a bunch of them. So in the next video, we'll try out a different simple logic function and see what sets of weights and biases work there. All right, that's enough for now. Thank you.